In this mass spec lab, we're going to look at a dipeptide solution using two different mass spectrometers. The first mass spec is a high-resolution Thermo Exactive instrument, and the source is on the left. The sample introduction valve here is on the right, a 6-port one, has a 2 microliter sample loop, and I'm going to fill the sample loop, overfill it. I've set up a simple method in which we're going to do a positive, two positives, two negative scans in recurring cycles. This here is the spectrum in real time, and what we're going to do is set up a data file dumping spot. So this is where we're going to dump the data, and we're going to start this. Sample loop is loaded. We have a place for the data. We're going to start. This whole run will be 4 minutes. We'll do 2 injections. Okay, injection 1 is started, and sample should be coming off, and right now it's doing positive, positive, negative, negative, positive, positive, negative, negative. Okay, and so right here in the negative we have a 263, and in the positive we have a 265. So, that lets us know that the molecular weight is 264. From just that nominal molecular weight, we know we either have phenylalanine-valine as one dipeptide possibility combo, or methionine-aspartic acid as the other. And the nice thing about this mass spec is that it's high resolution, so actually from the high resolution data we'll be able to eliminate one of those two choices. In order to avoid spurious results, we're going to do another injection. So it's always good to check these things. So in roughly 15 seconds, the sample loop will go back into its load position. I've loaded the sample loop again, and now it'll do a injection. And let's see if in about 10-15 seconds, if 263, 265 show up again. There we go, 263, 263, 265, 263, 265. We can see. So data collection will continue for another 70 seconds. And you might know, let's see, okay. And the data file, let's see, acquisition is going to stop now, so I am going to stop this part of the... Alright, so data acquisition is stopped. Let's take a look at the data. So, we're going to open that file. And in the top cell we have the composite TIC. In the bottom we have a spectrum. I'm going to add a cell into the view. Alright, and I'm just going to pick a particular scan almost at random. Alright, and so the negative is there. And there's a positive. So let's see, let's just zoom in on the cell here. So this is the negative, 263.14. Here's the positive, 265.154. And let's take a closer look at the high-resolution mass spec data for positive electrospray. And on the bottom cell here, we have our positive electrospray mass spectrum, and to hopefully increase the ability to distinguish vital information, let's examine a hard copy of the spectrum. Here we have the same positive electrospray mass spectrum. The protonated ion has an experimental mass to charge value of 265.15497. And for the presumed sodium adduct, we have 287.13684. And in electrospray, we also have a clustering effect in which, in this case, if M is the molecular weight is 264, then sometimes we'll see, depending upon concentration, 2M, a non-ionic, a non-covalent bonding, a 2M cluster plus the proton, a 2M cluster plus the sodium cation. And let's zoom in on these guys. Zooming in, we have our 265 M+1, our 287 M plus sodium cation, our 529 for the 2M+1, and our 551 for our 2M plus sodium. Now, high-resolution mass spec data actually gives us some additional information options. We can compare the actual observed data with what the data should be for given theoretical compositions of the molecular species. And thereby we can actually exclude possibilities. For the dipeptide with a nominal molecular weight of 264, we have three possible. One possibility is oxidized methionine-valine. This is our observed experimental data. This is the composition for oxidized methionine-valine dipeptide, and the difference between the two, between observed and theoretical, is 125 parts per million. If we examine the sodium adduct, or the presumed sodium adduct, again, this is our composition, theoretical composition, our theoretical weight, and the difference again, is greater than 100 parts per million. In mass spec terms, that's humongous. Another possibility is phenylalanine-valine. Again, we have our observed data, the theoretical composition for phenylalanine-valine with its theoretical weight, and the difference 1.1 parts per million. For the sodium adduct, again, in this case the difference is less than 1 part per million. Typically, for high-resolution mass spec data, you try to achieve confirmation within 4 parts per million. And the third possibility was methionine-aspartic acid. Again, observed theoretical composition, theoretical weight, difference in this case 262 parts per million. And if we look at the sodium adduct, the difference there is greater than 240 parts per million. So, by examining the high-resolution mass spec data, we can eliminate oxidized methionine-valine and methionine-aspartic acid as possibilities for this particular dipeptide. And if we examine those higher mass clustering peaks for presumed composition of methionine-aspartic acid, our experimental data was 529.30219. We have a C18 theoretical composition yielding 529.16326, a difference of 262 parts per million. For the presumed 2M plus sodium adduct, our difference is again over 250 parts per million. Confirmation that we're throwing out methionine-aspartic acid as a possible. If we were to look at the higher molecular weight end for a theoretical composition of oxidized methionine-valine, again, we would have, in this case, a difference of almost 125 parts per million. And for the 2M plus sodium cation cluster, we would have a difference of 120.4 parts per million. Again, ruling out oxidized methionine-valine as a possibility for the composition of our particular dipeptide. That leaves us with our final choice of phenylalanine-valine. For the protonated and sodium adduct down at 265, 287, we were well within a part per million. And here, for the 2M plus 1 cluster, we have a difference of less than 0.3 parts per million. And for the 2M plus sodium cation cluster, again, less than a part per million, 0.647 parts per million. For our negative electrospray, we have a simpler spectrum. And again, if we compare, if the theoretical composition is phenylalanine-valine, this is our observed, this is our theoretical, with our theoretical weight, and the difference is 1.6 parts per million, comparable to the difference we got with positive electrospray comparison. So with electrospray high resolution mass spec, we narrowed the possibilities down to phenylalanine-valine, but we don't know which amino acid is the C terminus. And that's going to be the job for the tandem electrospray. This is the front end of the SCIEX API3 Plus system. We have a syringe pump here with a 6-port injection valve, and then flow makes its way, and let's see if I can get a close-up of a needle. Alright, and so that is the nebulizing Electrospray needle. Right now the orifice plate is closed. Orifice plate is closed. Cryo head temperature is 16.3 Kelvin, and background pressure in the chamber is 10⁻⁸ torr. About 8 times 10⁻⁸ torr, and atmospheric pressure is 760 torr. Typically, nowadays, mass spectrometers do not use cryo pumping systems in order to achieve high vacuum. What I'm going to do is I'm going to open the orifice plate and get a flow of 30 microliters a minute of methanol water. Spraying, and let's take a look at the vacuum. Orifice plate has been opened, and you can see the vacuum instantly degrade to the low 10⁻⁵ torr range, which is what it should do, and temperature is climbing. It'll probably stabilize in the low 18 Kelvin range. And this is the Electrospray source with the vacuum, with the orifice plate open. And let's see if we can get a close-up. It's not going to let me focus that. The best I can do is closer. Alright. Flow is coming in on the right, on the left. Flow is coming in on the left, and the spray needle's on the right. And I think you can just about make out the spray residue on the plate is to the right of the orifice opening. The orifice itself has an opening of roughly 60 microns. Alright. So this is the instrument background. I have it scanning from 100 AM to 450 AMU, 1 AMU steps. Each scan is roughly 1 second, and it's repeating itself. It should be noted that over here what we have are the counts per second. So the most intense peak is this value, and everything else is normalized to the most intense one. So what I'm going to do is have the collision chamber with some argon nitrogen, 90% argon, 10% nitrogen. That's what SCIEX recommended in the for this instrument. And we'll take a look at what the product ion spectrum of... So let me go over the setup for the Tandem mass spectrometer for the SCIEX. The SCIEX is a triple quad mass spec, and it has the option of, you can have Q1 scanning and then Q2 and 3 acting as glorified lenses, or you could have Q3 scanning and Q1 doing something else. So in this setup, the ions are being formed via electrospray in the source, in the front of the mass spec. From that sample population of ions being generated in the electrospray source, then the job of Q1 is to just let through the ions in the precursor range. So it's going to be set to 263. And then depending upon the resolution, how wide that window or narrow it is depends. It's certainly, it's on the order of a 1 AMU, 1 to 2 AMUs. That precursor ion then enters the Q2 collision cell, and Q2 acts as the ion source then for Q3. And Q3 will be scanning from 10 to 310 at roughly 1 second interval scans. And that's a typical sort of MS experimental setup. Q1 lets through the precursor ion, Q3 scans the product ions. So for the product ion scan, the SCIEX is set up so that Q1 allows through just the ions in the range of 263, and Q3 is scanning from 10 to 310 at 1 AMU steps, roughly 1 scan a second. There's nothing magical about 1 second scans. It's just that that seems to be, it works out nicely for me. It's not too slow, it's not too fast. It works out well. Okay, so I loaded the sample loop, and I have a place for the data to be stored. The difference between R1 and R2 is the collision energy. In this case, it's going to be 12 eV. And let's see, we have a collision gas thickness of roughly 200, which works out to be about 4 millitorr. And let's start and see what happens. The data in real time, and I'm going to inject. This particular sample is after we've done a dozen other samples of other dipeptides, so there is some background. The 263 is showing up. Okay, and you can see that we have some 263 and something like a 147, 164, 115, 2 something. I bet it's a 219. I've got this as loss of 44. Right. So we're going to let these counts come down, and then we're going to boost the collision energy and see what happens to the precursor ion intensity and the product ion intensity. Alright, so this will probably take another minute and a half. So we'll close this run at, say, scan 200. Counts are already starting to go down. Good. let me close this portion of the video and I'll restart it with the newer. I've increased the collision energy to 18 eV. Collision energy in this case, difference between R1 R2. The previous run I let it run out to scan 250. So this one is going to be higher. And let me load the syringe and inject and start the save and it takes a while for the sample to make its way from the injection valve to the electrospray needle. And when it does, the count should start to increase significantly. Alright, so now we start seeing the 263 show up, okay? And we still got 219, 164, I'm guessing, 147, the 115. So these ions are more, the precursor has gone down in intensity because more of it is breaking up as it's hitting the argon nitrogen. And even has some of the 44. Right? So if this is negative, then the carboxylic acid side chain should be ionized, and we should get loss of like that. So if we get loss of CO2, we're going to get 44. Counts aren't as high as with the lower collision energy because we're getting more scattering. We'll close this file, let's say at, well, we'll let it run to 250. So I'm going to stop and then restart when we start. Alright, I've opened up the data file for the lower collision energy. Let me open up the data file for the higher one. This is our chromatogram, our total ion current, and now let's compare the spectra. And we'll set this full scale. So you can see as collision energy increases, the precursor ion drops down. We have our, let's see, for phenylalanine, the 91 is that aromatic side chain, the C7H6. So the 91 is the aromatic side chain, the C7H7, and then we have our 147 and 164, and that's indicative of phenylalanine at a C-terminus because the 147, 164 is that's the acene, and that's the D-1 and the Y+1 ions. We also have the 219, which would be the loss of the 44, and we also have the 44 showing up. So that's losing the CO2 and then just the CO2. Alright, so our choices were valine, phenylalanine or phenylalanine-valine, and this indicates that phenylalanine is in the C-terminus, so it's valine phenylalanine dipeptide.
And this is the temperature and vacuum as it's done collecting the data. So as you can see, when it's operational, the temperature is about 2 degrees higher than when it's blocked off and pumped down.
So this SCIEX API3 Plus, there are undoubtedly less than half a dozen still operational in the U.S. It's a vintage and a classic.
One of the disadvantages of a cryo-pumped vacuum system is that eventually you have to turn it off and defrost the system. So the practical runtime in which the SCIEX API3 is operational is about 20 hours. And then it has to be shut off and go into defrost mode. And then it gets pumped down. So all of the ices that were frozen out in the mass spec, then they melt, vaporize, and then the rough pump has to pump it out.